2022 GMC Hummer EV. 25. Supply chain. The electric vehicle supply chain comprises the mining and refining of raw materials and the manufacturing processes that produce lithium-ion batteries and other components for electric vehicles. The lithium-ion battery supply chain is a major component of the overall EV supply chain, and the battery accounts for 30–40% of the value of the vehicle. 26. Lithium, cobalt, graphite, nickel, and manganese are all critical minerals that are necessary for electric vehicle batteries. 27. There is rapidly growing demand for these materials because of growth in the electric vehicle market, which is driven largely by the proposed transition to renewable energy. Securing the supply chain for these materials is a major world economics issue. 28. Recycling and advancement in battery technology are proposed strategies to reduce demand for all materials. Supply chain issues could create bottlenecks, increase costs of EVs and slow the uptake. 26. 29. The battery supply chain faces many challenges. Battery minerals typically travel 50,000 miles from where they are extracted to downstream manufacturing facilities. Deposits of critical minerals are concentrated in a small number of countries, mostly in the global south. Mining these deposits presents dangers to nearby communities because of weak regulation, corruption, and environmental degradation. These communities face human rights violations, environmental justice issues, problems with child labor, and potential generational legacies of contamination from mining activities. Manufacture of battery technology is largely dominated by China. Life cycle of lithium-based EV batteries. Schematic of life cycle of EV batteries. Adapted from Engel et al. 30. There are mainly 4 stages during the life cycle of lithium-based EV batteries: the raw materials phase, the battery manufacturing, operation phase, and end-of-life management phase. As shown in the schematic of life cycle of EV batteries, during the first stage, the rare earth materials are extracted in different parts of the world. After they are refined by pre-processing factories, the battery manufacturing companies take over these materials and start to produce batteries and assemble them into packs. These battery packs are then sent to car manufacturing companies for EV integration. In the last stage, if no management is in place, valuable materials in the batteries could be potentially wasted. A good end-of-life management phase will try to close the loop. Used battery packs will either be reused as stationary storage or recycled depending on the battery state of health. SOH. 30. The battery life cycle is rather long and requires closer cooperation between companies and countries. Currently, the raw materials phase and the battery manufacturing and operation phase are well established. The end-of-life management phase is struggled to grow, especially the recycling process, mainly because of economics. For example, only 6% of lithium-ion batteries were collected for recycling in 2017–2018 in Australia. 31. However, closing the loop is extremely important. Not only because of the predicted tightened supply of nickel, cobalt and lithium in the future, also recycling EV batteries has the potential to maximize environmental benefit. Zhuo et al. Predicted that in the Sustainable Development Scenario, lithium, cobalt and nickel will reach or surpass the amount of known reserves in the future if no recycling is in place. 32. Sears and Whitaker found that by deploying battery recycling, some greenhouse gas (GHG) emission from mining could be avoided. 33. Battery recycling emissions under U.S. average electricity grid. AB, for cylindrical cell, and CD, for pouch cell. Adapted from Sears and Whitaker. 33. manufacturing process of EV batteries. To develop a deeper understanding of the life cycle of EV batteries, it is important to analyze the emission associated with different phases. Using NMC cylindrical cells as an example, CS and Whitaker found that around 9 kg CO2 per kilogram battery 1 is emitted during raw materials pre-processing and battery manufacturing under the use average electricity grid. The biggest part of the emission came from materials preparation, accounting for more than 50% of the emissions. If NMC pouch cell is used, the total emission increases to almost 10 kg CO2 per kilogram battery 1, while materials manufacturing still contributes to more than 50% of the emission. 33. During the end-of-life management phase, the refurbishing process adds little emission to the life cycle emission. The cycling process, on the other hand, as suggested by CS and Whitaker, emits a significant amount of GHG. As shown in the battery recycling emission plotter and C, the emission of their cycling process varies with the different recycling processes, different chemistry and different form factor. Thus, the net emission avoided compared to not recycling also varies with these factors. At a glance, as shown in the plot B and D, the direct recycling process is the most ideal process for recycling pouch cell batteries, while the hydrometallurgical process is most suitable for cylindrical type battery. However, with error bars shown, the best approach cannot be picked with confidence. It is worth noting that for the lithium iron phosphates, LFP, chemistry, the net benefit is negative. Because LFP cells lacks cobalt and nickel, which are expensive and energy intensive to produce, it is more energetically efficient to mine. In general, in addition to promoting the growth of a single sector, a more integrated effort should be in place to reduce the life cycle emission of EV batteries. A finite total supply of rare earth material can apparently justify the need for recycling. But the environmental benefit of recycling needs closer scrutiny. Based on current recycling technology, the net benefit of recycling depends on the form factors, the chemistry and their cycling process chosen. Manufacturing. There are mainly 3 stages during the manufacturing process of EV batteries: materials manufacturing, cell manufacturing and integration, as shown in manufacturing process of EV batteries graph in gray, green and orange color respectively. This shown process does not include manufacturing of cell hardware, I.E. casings and current collectors. During the materials manufacturing process, the active material, conductivity additives, polymer binder and solvent are mixed first. After this, they are coated on the current collectors ready for the drying process. During this stage, the methods of making active materials depend on the electrode and the chemistry. For the cathode, 2 of the most popular chemistry are transition metal oxides, I.E. lithium nickel manganese cobalt oxides, LiNMC, and lithium metal phosphates, i.e. lithium iron phosphates, LFP. For the anode, the most popular chemistry now is graphite. However, recently there have been a lot of companies started to make Si-mixed anode, Sila Nanotech Prolodion, and Li metal anode, Cuberg, solid power. In general, for active materials production, there are 3 steps: materials preparation, materials processing and refinement. Schmuchert et al. Discussed materials manufacturing in greater details. 34. In the cell manufacturing stage, the prepared electrode will be processed to the desired shape for packaging in a cylindrical, rectangular or pouch format. Then after filling the electrolytes and sealing the cells, the battery cells are cycled carefully to form SEI protecting the anode. Then, these batteries are assembled into parts ready for vehicle integration. Quaidit et al. Discuss the overall battery manufacturing process in greater detail. Reusing and repurposing. When an EV battery pack degrades to 70% to 80% of its original capacity, it is defined to reach the end of life. One of the waste management methods is to reuse the pack. By repurposing the pack for stationary storage, more value can be extracted from the battery pack while reducing the per kilowatt-hour life cycle impact. However, enabling battery second life is not easy. Several challenges are hindering the development of the battery refurbishing industry. First, uneven and undesired battery degradation happens during EV operation. Each battery cell could grade differently during operation. Currently, the state of health, SOH, information from a battery management system, BMS, can be extracted on a pack level. Getting the cell state of health information requires next generation BMS. In addition, because a lot of factors could contribute to the low SOH at the end of life, such as temperature during operation, charging forward/discharging pattern and calendar degradation, the degradation mechanism could be different. Thus, just knowing the SOH is not enough to ensure the quality of the refurbished pack. To solve this challenge, engineers can mitigate the degradation by engineering the next generation thermal management system. To fully understand the degradation inside the battery, computational methods including the first principle method, physics-based model and machine learning-based methods should work together to identify the different degradation modes and quantify the level of degradation after severe operations. Lastly, more efficient battery characteristics tools, for instance electrochemical impedance spectroscopy, EIS, should be used to ensure the quality of the battery pack. 35, 36. Examples of storage projects using second life EV batteries. Adapted from a 1:35 second, it is costly and time intensive to disassemble modules and cells. Following the last point, the first step is testing to determine the remaining SOH of the battery modules. This operation could vary for each type system. Next, the module must be fully discharged. Then, the pack must be disassembled and reconfigured to meet the power and energy requirement of the second life application. It is important to note that qualified workers and specialized tools are required to dismantle the high weight and high voltage EV batteries. Besides the solutions discussed in the previous section, a refurbishing company can sell or reuse its discharged energy from the module to reduce the cost of this process. To accelerate the disassembly process, there have been several attempts to incorporate robots in this process. In this case, robots can handle more dangerous tasks, increasing the safety of the dismantling process. 35, 37. Third, battery technology is non-transparent and lacks standards. Because battery development is the core part of EV, it is difficult for the manufacturer to label the exact chemistry of cathode, anode and electrolytes in the pack. In addition, the capacity and the design of the cells and packs changes on a yearly basis. The refurbishing company needs to closely work with the manufacturer to have a timely update on this information. On the other hand, government can set up labeling standard. 35. Lastly, the refurbishing process adds cost to the used batteries. Since 2010, the battery costs have decreased by over 85%, which is significantly faster than the prediction. Because of the added cost of refurbishing, the refurbished unit may be less attractive than the new batteries to the market. 35. Nonetheless, there have been several successes on the second life application as shown in the examples of storage projects using second life EV batteries. They are used in less demanding stationary storage application as peak shaving or additional storage for renewable-based generating sources. 35. Recycling. Examples of current lithium-ion battery recycling facilities. Adapted from a 1.35. Although battery lifespan can be extended by enabling a second life application, ultimately EV batteries need to be recycled. Recyclability is not currently an important design consideration for battery manufacturers, and in 2019 only 5% of electric vehicle batteries were recycled. 38. BEV technologies lack an established recycling framework in many countries, making the usage of BEV and other battery-operated electric